Hey, trust me, I am a developer. Thank you for the follow. I think I know who are you. I am not a medium, I am just half an idiot. Alright, it's time to get started. So, let's see our task board. Past week we have done a lot of new tasks and we have advanced until half of our goal in the completion of the instructions. So we have all the first row, half of the second row, and some stuff on the last row, and we are halfway through to having all the instructions of the 5502 chip. The next one I want to continue working with is increase and probably also decrease. We can probably work on both at the same time. Do I have a unit test for decrease? I think not. So I will add also implement decrease. So a little reminder, we have our CPU class with a lot of registered instructions. Each instruction has different memory mapping methods or different registers accessing. So there is a lot of reusability in this code. So the next step is figuring out what does increase and decrease do. We already have increase X and increase Y, if I remember correctly. Yes, we have increase X and increase Y. So we are going to add increase now. So to that, we are going to first add a test. Okay. Let's create a new script, selecting the type to be was it base test? Sorry. Right. So that I can choose select the template. Sorry about that. I entered yes. It's already selected the template. And I will name it increase, and it have created our file, and I can just add a new node. I name it increase and place it just over LDA, follow the same layout. Let's see what are the accessing modes of increase. So increase can use 0 page X, absolute and absolute X. So we don't need immediate, we don't need absolute Y, and we don't need any of the indirect ones, so we can get rid of them by goodbye Goodbye. And also, let's do this. Let's place our documentation in the side next to our editor, so we can take a look at both at the same time. So it's 0 page X. Let's move up. Absolute and absolute X. Let's make all of this lowercase. And let's put a ring on it. No, really, let's put the name of the function, which is increase memory value. And now let's fill information about the opcodes of each of the instructions. 0 page is E6. 0 page X is F6. Wait, sorry about that. So I inverted the upper hand but not the lower hand. Okay. F6 for 0 page X. Double E for absolute. And FE for absolute X. So the way this is meant to work is each time you call this function, it increases the value of the memory read in the next byte by 2. So let's copy a template code from, I don't know, LDA maybe. Oh, I don't see LDA in here. Let's find it here. Yes, let's copy this content and go back to increase. Hey, what happened with the text I copied? Alright. So this code should increase the value of some memory mapping, right? And set the negative and 0 flag. We don't care about overflow flag. We don't care about hard flag. It just increases and wraps around the value. So let's create some memory examples. Hey Cricket, how are you? You made it. Hey, welcome very much. So nice to have you around. Let's move this so it's maybe a little more visible, like in here. Okay. For my own sake, I am making the messages always visible, so I can see them in the stream a little longer. You too? I am not a tool. So I am right now writing a little assembly code with assembler to test the functionality of the increased memory value instruction. So first of all, I need some base memories to test the final value after. So let's do CPU and memory, and we can do memory write, and we can write some memory. Like, let's take for example the location 3, and we are going to store a value. So in this one I want to store 09, and when I increase it, it should be a 0A. And this other one I want to put FF. So when I increase one, it should go to 0. And in 0.5 I will also store FF, but I will increase it twice. So this is the test plan. We are going to test these 3 values and see if the flag for all of the 3 of them matches. So the instruction for 0 page accessing is 0x0006, and we are going to increase the value in this memory location. We are also going to increase the memory on 04, and we are going to increase the value of the location 05 twice. So that this is what we are going to test, right? So the first assertion is we want to read the memory from 03, and it should be 0A. Oh, it's U2, not U2. Oh, I have a very bad citing issues. Not too many instructions, lots of hardware to emulate those, right? So yeah, so the list of instructions is quite small, but each of the instructions has 1 to 7 or 8 variants. So in example, add with carry is like you add and you take away the extra bit if you have superseded the byte overflow. But you have many ways of selecting what memory you are adding to. Like you can set, okay, this is the value that I am adding, or the value is stored in the memory, or the value is stored in the memory plus an offset, or the value is stored in a memory but 2 bytes are used, or 2 bytes are used plus an offset, or 2 bytes are used plus an offset but read the offset from another place. So there is a lot of variants for the same instruction, and that makes it much longer than we actually needed. Anyway, so this is our test code. This adds 1 to memory location 3. This adds 1 to memory location 4. And this will add 1 2 times to memory location 5. So we want to now test reading the memory. So CPU memory, memread, and we are going to read the address 0x03, and we want to make sure it equals 0x08, which is 0x09 plus 1. This one is not 0, so 0 is gonna be false, and this one is not negative, so negative flag is false, because it is only negative if the leftmost bit is a 1, right? So the other 3 tests is testing the other 3 memory addresses. So I am doing something wrong here, and that is that the flags will only update for the last value. So I will have to split this in many parts. So the first part will only testing the increase of the 03. I already found a bug. The second part will only test increase the value of the memory 4. And we are going to test 4 equals to 0, because FF plus 1 is 0, and it is 0 but not negative. And the last one, oops, I should not have deleted everything. We'll copy this and redo my stuff. And the last one will add 1 to memory 5 twice. So this one is not 0 and is not negative, and the value of memory 5 should be a 1. Does that sound correct? We can add, just for the sake of completion, another one with memory address 6, and we can test the case where a positive turns into a negative. So we can write OB for binary and put the first byte on a 0 and the rest on ones. 1, 2, 3, 4, 5, 6, 7. So when we add 1 to this, all of this will turn a 0 and it will turn the first bit into a negative. So when this happens in our test here, adding 1 to 6, when reading memory stick, the value that we want to read is meant to be the opposite of this, casually. 1, 2, 3, 4, 5, 6, 7. It is non-zero, but it is indeed negative. So this is the test for immediate increase of the memory page. I don't know if you have followed it. Was it too fast? So we have our base case example, and now we need to re-implement it for the other addressing mode. So 0 page X is more or less the same, except it adds an offset to the value that we pass. So let's say we are going to add an offset of 3 to whatever values we are setting here. So to all of these memory mappings, I will say I will add an offset of 3. And what I am going to do before doing this cause for all the tests, I will first load a value of 3. For that I am going to use LDA, which is A9 instruction, and we'll load a 3, 0x03, and then I will transfer that value to the X register using tag, which is OXA9. So in theory, capitalism works, right? I just want to say thanks all, your help, it is invaluable. Okay. Thank you so much for appreciating it, and thank you so much for being here. It's important to me to have someone to talk to more than having audience. It makes this much more bearable, really. I enjoy a lot the company of people. Okay, next test is, I spotted an issue here. So we are testing 0 page X, but we didn't change our instruction. So the instruction for 0 page X is F6, but we are still using E6. So we have to change all of them. Okay, spotted it right on time. Okay, back to the test. We have tested 0 page. We have test for 0 page, for 0 page X, and next goes absolute. Absolute is basically the same as 0 page, but it has a 2 bytes address instead of 1 byte. So what we are going to do is use an address of 2 bytes So we are going to use 40, 03, or 405 and 06. And we are also changing what is the opcode to access it. So instead of E6, we are going to use EE. 1, 2, 3, 4, 5. And for the address, because the NES is little endianness, we have to put first the less significant byte and then the most significant byte. That means after each of these, we are going to add the OX40 value. So it will read the less significant 03 and then the most significant 40, and will access to the right memory that we want to test. And finally, absolute X is the same difference that we have made for page 0 page X. So first, before I forget, let's change the instruction. EE for FE. And let's add an offset this memory +3, and let's also load and transfer the offset to our X register in all the tests. Oops, I set up that. I will fix it like this. Paste. So it loads a 3 and transfer it to X register. I feel the same. I am sort of alone in the real world when it comes to programs and developers. So yes, that was kind of one of the reasons why I am doing this. So for a little context, I am for a long time doing therapy, and this is kind of a way that I am trying to find for myself to communicate with people, and also to find myself and finding projects that I find fun doing. And the NES emulator caught my attention from the start. The other guy around trusts me. I am a developer. We know each other. He's a teammate from work, and he knows before looking at the NES, we both have been looking at the SID80 CPU processor, and messing around with some assembly code, trying to make a game for the SID80 and stuff like that. And he even made a chip 8 emulator, I think on, what was it, Rust? And I don't quite remember. So I had this idea of making an emulator inside Godot for a long time, but I never got the codage. Oh, it was on C. Okay, thanks. I never got the codage before to make it happen. So taking some propulsion for saying, how do I say it? I don't know the term in English. So I am taking some codage from the strings from Else Dragon. So because he's doing that awesome NES game, it kind of clicked and say, okay, this is my chance to make something that is worth for someone. I at first I just wanted to make a tool for him to make animations, but then I realized that, okay, I need to read the files anyway, right? So why not just make the emulator first, so I will have the part that loads the room before actually creating the tool, right? And it just came together a little bigger and bigger, and it just jumped up. So let's do the increase command now that we have a test. We don't yet know if this test passes, but we will find out pretty soon. So let's find our close on test file. Okay, here is our NES CPU. So increase is right before increase X. So I will tag the opcode and will duplicate this line to have increased defined. So we don't yet have a function. So I will comment this and let's create our function before I forget that. So this was increment register. Okay, so this was not actually increased, it was in X, in Y. And for increase we are going to make a func increment memory we are going to take an addressing mode. It only takes an addressing mode. It doesn't take any register or any value, but I also want to pass the value that we want to increase or decrease. So we can use the same function increment memory for also the decrease command. So for increment we are going to pass +1, and for decrease we are going to pass -1, and it should work on both, right? Also, I live in a bubble where not for the online contact I wouldn't know any dev. It is nice the internet let us pursue our passions and share them with others that have them. Yeah, that's right. So first of all, we want to know what memory we are addressing to. So let's get our address. Oops. Copy from here and paste. And now with addressing mode we will know what is the address. Sorry. Let's do var. Yes. So this is address. And now we can get the real address using a memory read. With address. So address is the pointer for saying so. An address is the actual address we want to increase. Is that right? Question. Actually, no. Address. Okay, so 0 page will read the second byte. That second byte is the actual address. Okay, so sorry about that. I am confused. Let me think about it. I have got to put the kids to sleep. Okay, say duel to mini cricket from my part. So, how are you differentiating high memory from normal one so you can have accurate emulation? So the answer to that is I don't. I am just making the CPU instructions, and whatever the memory is being stored depends on what the loading or the initialization of the function works like. So I have a base class for the CPU, and the CPU has a memory that is null by default, and a program counter, which is the memory address for what is the current instruction, but it has a set of load and run packets. So load and run takes care of where the program is stored. So the program is passed as a packet byte array, and that's an array of 8 bits integers, and particularly the NES loads that memory starting on memory address 8000, which is, if you look at the memory map, is where the prog ROM is stored. I cannot find the right picture. Can you show me a picture? Nope. Okay, here it is. So from 00, the first 2000 is the CPU RAM used for real operations. This is where 0 page is located, the first 256 or something, and the rest of the stuff. Then there are input-output registers. I don't yet know what are them, but I think it is the PPU and the ALU RAM. Then is the expansion ROM, which is some memory that is what is the word, exclusive, like it is mapped for some extra memory that can be or not on the cartridge. So it depends completely on the hardware that was used for the program. And then it's the save RAM. The save RAM is where you would put your save file, and it is actually, if I am not wrong, read-write. So if you put something into the save RAM, it is going to be saved into the cartridge as long as the battery of the cartridge works. And then in the 8000 up to the complete memory size, it is the program ROM, which is the read-only byte code that has the actual game code. So the way the NES works is that when you insert the cartridge, it will start an interrupt that will put the program counter in whatever value is stored inside FFFC. So by default it will start on 8000, but the ROM can change it to actually have a different value where the program is going to start, and that kind of depends on the hardware and the ROM. But on a real NES, the 6502 he access to fast memory which runs faster than the usual one. Yes, that is the 0 page. It is much smaller. I think you could simply check if the address is under address code to make the CPU take a lower or faster access. Well, that is actually the differentiation using zero page, which is the first 255 memory addresses up to FF, or using absolute, which takes 2 bytes, and because it takes 2 bytes and has to load a lot, it takes more cycles of the CPU to locate in that memory. So yes, it is all considered in this code. Addressing mode is what makes the access of memory for read or for write faster or slower. And in our table, here in the reference, it shows you that particularly for increase, zero page takes 5 cycles to access and modify the memory, and absolute takes 6 cycles to address and modify the memory. I/O is where you get access to everything on the device: CPU, joystick, even switching banks or interacting with the MMC chip inside the cartridge. I don't yet know what is all of that, so I will figure out one step at a time. So we read the instruction, we are getting a value from an address. We are getting an address. From the address we get the value, and that is the address that we want to access. So yes, I think we are correct here. So first we get the address, and then we get the actual address we want to modify. Next is what is the value we want to modify. Memory, memread, address, bar result is gonna be value plus amount. And now we have to do the wrapping for this value. So if result is bigger than 0xff, result minus equal 0xff. Else if result is less than 0, result plus equal OXFF. So basically the idea here is fake the 8 bits result using this. And after that we can just update negative and positive values. Update seed and end flag passing result, and also we want to write the value, the result value on the memory. So memory, memwrite, address is gonna be address again, and and result is the value that we want to store. So now we can use increment memory to register our opcode. Increment memory takes 2 arguments. The first argument is how much you want to increase or decrease your memory, so it's gonna be a 1. And the second one is what is your addressing mode. So we are going to pass 0 page. So let's duplicate this a couple times. And let's see our table of values again. So it's 0 page, 0x, absolute, and absolute x. All of them will increase by 1. The first 2 takes 2 bytes. The last 2 takes 3 bytes. And it is 5 cycles, 6 cycles, 6 cycles, 7 cycles. And now all that is missing is setting the opcodes for each. Where is my music? Zero page is E6. Zero page X is F6. Absolute is EE. And absolute X is FE. So now, if I am not totally crazy, we are ready for testing. We have created the test, we have added the test, we have implemented the opcode and registered it. That is all the steps for creating an instruction. And it failed, for surprise of no one. So let's see what is our memory inside the CPU. CPU, memory, and let's see the bytes. And none of them have changed. So we did something wrong when accessing our memory. So memory, I was wrong and should not have used the address. Instead, let's choose address and forget about this. Let's comment it. Okay. And let's see if it all works. We'll put a breakpoint here and see what is inside value when running. And value is a 9, so indeed address is the 3 that we wanted to read from, and value is the value that we wanted to increase 1 to. So let's continue. And the first test passed, but the second one failed. So what is memory in memory slot 4? Let's check the CPU. Let's check the memory. And in 4 we have 1. And why is that? So if the result what I am doing wrong. Any ideas what I am doing wrong? So Let's try with the calculator. So we have FF plus 1 minus FF. It is okay, so it is not minus FF, it is minus 0x0000, and probably the same with this. So if I try a decimal minus 1, it is this value. Okay, it's a 64 bits, but let's try to make it work right. And for some reason I cannot write properly, but we are going to test it and see what happens. Okay, it failed trying to read an instruction. And it tried to read 3 as an instruction. It's load 3 transfer, and this one should take 2 bytes, F6. So this is increase 0 page X. So this smells like I made a mistake registering the number of bytes that it takes. But no, I said that it takes 2 bytes, and that is correct. So what is wrong with you? Current PC is 32773. Well, I am not sure of any other way finding what is the program counter other than looking at the memory. So we have to go to the memory address, and this takes 20 values at a time. So we need to divide this by 20. It's 32773 divided by 20, and it's 1638. Oh, I cannot change. Oh, here it is. 1638. Memory should be around here. Okay, here it is. So wait a second. CPU memory 1638, was it? Okay, so 169 3 169 again. Oh, and why is that? It is supposed to be transferring to X. What did I do wrong? Oh, that is AA. Okay, that was the issue. Okay, transfer is AA, not A9. That was a mistake on my part. Okay, let's give it another shot. Okay, it failed, but at least it failed on the test and not when accessing the memory. Right, so it is trying to access the 3 memory instead of the 3 plus offset. So all of this should be accessing the memory plus the offset of 3. And the same is going to happen for the absolute plus X. Give it a shot. Okay, something went wrong, and this time it failed on 0 page X on the last one. So load a 3, transfer to X, and then try to increase one on 6 plus 3. Aha. So the increase in this case did not work as intended. And why is that? What is in memory? Because it worked in this one. Why did it fail in this other one? Oh, because I did not change this opcode. Okay, another shot. Okay, 0 page works. So now we have to figure out absolute. And yeah, we have forgotten to change the memory as well. So all of these tests should start on 0x40. And all of these other tests should start on 0x40 as well. And this one has the plus 3 added. So give me another shot. Okay, this is absolute, and we are trying to check if 4005 is 1, and it is not. And the reason is because we only passed 1 byte to this opcode, so we are missing this 0x40, and most probably it's also happening on absolute X. Yes, indeed it is. And now it passes. Yay! So we forgot to put our print for success cases. So let's also add that print. And let's rename the function. And let's give it another shot. And now we have increased tests passed properly. So with this in place, it is pretty much straightforward to make the decrease instruction. So the decreased instruction, here we go. subtracts 1 from the value held at a specific memory location, setting the 0 and negative flag. So it is the same, except it subtracts instead of adding. And this is why I implemented our instruction like this, because now we can take all of this, duplicate it, and change increase for decrease, and change 1 for -1, and update our opcode, and that should be all. Famous last word. Can you show me that? Yes, this. Hey. So decrease takes 0 page, 0x, absolute x, and it is C6, D6, CE, and DE. 2 bytes, 2 bytes, 3 bytes, 3 bytes, 5 cycles, 6 cycles, 6 cycles, 7 cycles. Same of all of these. So this should be all for implementation, and now we only need to create the test. So for creating the test, I will duplicate the increase test. I will name it decrease, and it's just on top of increase. We'll add a node, call it decrease, and assign the script, save in, and now we can change the code to make the test actually useful. So let's rename all increases for decrease. And let's find all memory and instruction name. Let's call it decrease, and do the same with all the instruction signatures. Delete, name it decrease, and now we can fill the actual opcode for the real ones that we are meant to be using. So 0 page is C6, fault 0 page X is D6, fault absolute is CE, fault, and absolute X is DE. Okay, so now we need to update our test, considering that it is going to decrease instead of increase, right? So the instruction for the first one, we have to replace OE6 for C6, OX C6, and let's replace them. 1, 2, 3, 4, 5, and add to the print. Not that it matters. We are going to fix the print later anyway. And for this one, 9 minus 1 is going to be 08. We can probably do, I don't know, A0 minus 1 is gonna be 0. No, sorry, 9, 0, 9A, right? I think. Whatever. If we subtract 1 to 0, 0, we are meant to find FF. And if we subtract 2, actually this one does not matter, so we can get rid of the entire part. And if we subtract 1 to this, we are going to find the same value with a 0 at the end. I think the point... Wait, let's get this and let's put a 1 in here. So the second test should be a 0. And this is the one that we probably do not care. Or we can invert values. Yes, let's do that. Let's invert values. So we are subtracting 1 to negative 0 in this case and getting this value. So this one, let's check the flags again. So first one, this is not negative, it's not 0. This is not 0. Oops. But it is negative because F has a 1 in the 8-bit. This one is a 0 and not false. And this one is no negative and no 0. So we can test this one for now, making sure it works. I will add a return on each of these other tests for now. And let's give it a shot. And we see it failed in this one. A1 minus 1 should be 9F, not 9I. It's 9F. Okay. And 9F. Wait, what? 9F is indeed negative. Wow, I did not know that. Okay. Okay. So 0, I subtracted 1 and expected to see a double F. But it is not a double F. So what I am doing wrong? What is in memory 4? Aha. So it's not 255, it is 254. So I am adding or subtracting. I am making a mistake in my warp in. So if it is less than 0, I am adding FF, and I should be adding this value. instead. So let's give it another shot. Okay, now it passed that one. And this one that is subtracting twice. It's a 1 subtracting twice. And this one should also be FF in this case. Right, I am subtracting twice. I will put a 2 in here, because I already tested the wrapping around. So yes, it passes now. So I think it will be more useful if I just delete this code and make the other variants again. Probably. Or do I just need to update the memories and opcodes? Yeah, let's do that. Let's go one at a time. Memory. Let's take all these values and let's put them in these other places. Let's take all the F6 and put the D6 for the instruction. 1, 2, 3, 4, 5. Is there one more? Ah, the printing. So what is next? The values result 9F, FF, 0, and this binary number. And the next is the flag. This one is not 0 but is negative. This one is not 0 and is negative. This one is 0 and not negative. This one is not 0 and not negative. So, can we trust this test? Let's give it a shot. Okay, it passed. So we have increased and decreased running and passing for 0 page X. So now we have to fix it for absolute. For that we are going to copy the memory values again and paste them on the absolute. We are going to replace the opcode. It used to be OXEE, and now we are going to change it for OXCE. 1, 2, 3, 4, 5, 6. We want to change the output result 9F. So let's fold this so we can see better. First one is 9F, second one is FF, third one is 0, and last one is this almost negative value. And we want to update the flags again. So this one is not 0 but is negative. This one is not 0 and is negative. This one is 0, but not negative. This one is not 0 and not negative. Let's rename the print and give it a shot. And seems to have passed. We have decreased. Okay, it did not run, and that is because I forgot to delete the return in the top. Okay, once again. Decrease absolute has passed. Okay, awesome. One more to go. Let's copy the memory values for our test. Paste them. Let's change the opcode. So now it is DE instead of FE. 1, 2, 3, 4, 5, 6. And let's change the result of our memory read. 9F FF 00 and this binary number, and update the flags. This is not 0, it is negative. This one is not 0 and is negative. This one is 0 and not negative. This one is not 0 and not negative. Delete the return, change the print, and give it a shot. Okay, failed. And this one is negative. Indeed. One more shot and it passes. So yay, we have increased and decreased all the four memory addressing modes. Yep. Lot of work. It's time for the commit. Git status. So we have new test. And let's take a look here. We added increase, we added decrease, the opcodes are correct, memory mapping is correct, the bound offset is correct, the number of cycles and bytes is correct, and the function for increment memory. And this is just adding the two tests to the testing. Let's commit it. Implement inc and tick opcodes, create unit test. Aha! I forgot to say let's make an issue for all of these. So this one closes 24, sorry, 22, 23, 23, 24, 25, all of them. Git push origin main, and let's see if that kind of comment works. Okay, it only closes 22. Alright. So now I know. So we've made increase and decrease, and we already have increase X and increase Y, and this is more or less equivalent, is decrease X and decrease Y. It should, okay, it's undone. So let's make a unit test for this. This will be the last instruction we do for today, because we have been already 1.5 hours online. Nice work so far tonight. Thanks, Cricket. Are you enjoying the work, the stream? Let's make a new script and call it text. So let's take a look at the reference for text, and that only takes one addressing mode, which is none. So that makes actually much easier to test it. And it updates the same two flags. So actually we can probably so did we have in X and in Y test? No, we did not. We never tested it apparently. So what do we do with this? Do we make all of them in a single one? We're going to make this is CA text decrease register X decrease register Y. So it is CA and 88. Where is my music? Copy and paste. Funk. Paste. Okay, So I can rename this one text day. What is rename? Text day, and I can duplicate it and name it inX in Y, and do both tests at the same time in different scripts. So before I forget, I will just rename stuff. This is in X and in 1, and this is increase, and this needs their actual opcode, but I will leave it like this for now. Decrease X, so let's take the LDA, no, actually the tax test, and let's make a couple of passes on it, so we can load a 10, transfer it to X, and decrease it. And this will be a 9, not negative and not 0, and we can load a 1, transfer it to X and decrease 1, and this is meant to be a 0. It is 0 indeed and not negative, and we can load a 0. Let's try to keep formatting, and this is OXOA. OXO. Okay, and this one is 0. No, sorry. This one will be FF. Theoretically, it is not 0, but it is negative. And this is the test that we are making. Let's copy it and paste it, and let's just change the decrease of X to decrease of Y, and let's change the transfer to X to transfer to Y. And this test should check the Y register instead of the X register. And we need, of course, our print. Print function name space function name space, and you should be right after increase. So let's add a node. Call it in X. No, you are not increase, you are decrease X, decrease Y, and goes right after decrease. Okay, awesome. And now let's make a similar test for increasing. So I will copy this for decrease x, and I will put it on increase x. So now let's take a look and find out what we was missing for increase x. Pa-pa-pam. So increase x uses the E8 opcode. E8. And we need to change, yes, the C8 for E8. And we are going to copy the decrease and paste it. This one is named C8. And if all three of these needs to be OX C8. And now we have to check what is the value of increasing 1 to all of these. So this one is gonna be OV instead of 09. 1 plus 1 is 2. So I assume this one should be FF plus 1 is gonna be 0. And this one yes, is FE, right? FE plus 1 is FF, and it is not 0 and it is negative. So increase is ready to be tested. Decrease is not, because we have not implemented it. So we are making an early return here, but we are going to add the increase one. So new node is in X in Y, the increase, and let's assign the increase script. And in theory, because this was implemented at the start of the chapter, we should be able to run it, and it did not pass. Let's see, what did we do wrong? So we are loading OA, transfer to X, and increasing it by 1. Right, and it is increasing, not decreasing, so it OV. Right, I fixed these values but not the other. This is in Y, not in X. Nice shot. So FF 0, FE, FF, and this is FF will result 0 and FE will result FF. Another shot. Okay, it was just dumb copy paste mistake. So in X and in Y has passed. We can now remove the return and do the actual implementation of decrease X and decrease Y, which, by the way, I also made the mistake of the function naming here. Oops. So, NES CPU. Let's see how I made increase X, increment register. So I can add a B amount value in this one and make the same operation in here. So instead of doing bitwise warping, we can make this same instruction, because now we have negative case, and the negative case needs you cannot use bitwise operations because it is a 64 value. Before it was just adding, so it was always positive, but now this one needs a special use case. So this is just register value equals val after it has been warped. So inc x, in y, dx, dy. We can add decrease x and decrease y to our mapping. Right. Where should it be located? I am a little confused. Let's see our memory mapping here. Decrease is actually after compare. Okay. Let's put them together with increase. Otherwise I will become confused. Dex day, copy in x and turn it into dx. Now the increment register for x and 1 is gonna pass a 1 as first argument, and for decrease it's gonna be a -1. Before I did increase before decrease, so maybe I will invert it. Yeah, so I keep the order at least. So decrease x is CA, and decrease y is 88, and this one takes register y -1, 1 byte, 2 cycles, all the same as increase. So are we ready for testing this? I think so. Okay. Increase x, increase y passed, decrease x, decrease y passed. So yes, it's working. Implement x and say convert ratio status it adds everything inside the test folder. It's adding part. Want to check this? And I added a new bin, I added text with the right opcode, and use the increment register with a negative first argument in X and Y. This looks correct. And I changed this to have an amount argument, and added the test to the thing. Git commit, implemented text and the opcode, added unit test for them, added unit test for in X and in Y. Close the... What are the numbers 26 and 27? Closes 26, closes 27. Oops. Alright. Git push origin name. And we should be done with this. Yay! So, what do we have now? We have done all the first row. We have done clear flag for this. We have done comparing. We have done decrease X and decrease Y. And we have increase X, increase Y. So from the second row, we are only missing A or E or R and jump. From the second line, we have LDA. And I think nothing else. And from the last row, we have setting all the flags. We don't have set X and set Y, but we have tag type. So I think we are somewhere around 60%, something like that. So thank you for watching. We are just a little closer to our goal. See you again next stream on Saturday, or maybe earlier if I want to make a bonus stream making unit tests. But as you can see, it is basically impossible to make the test before the implementation of the instructions. You have to do both of them at the same time. Good night, Cricket. Thank you so much for being around, and thank you so much for staying until the end. I appreciate it really much. Bye.